Another very popular situation. So the rate of growth, dNdt, that denotes the amount of how much of a population of the population size is changing with respect to time. Well, if we integrate that function, well, that derivative within time 1 and time 2, that's going to tell us about the net change, how much of the population change, of the population size change within between T1 and T2. And another very common in economics, for maybe some of you are economic majors taking this three calculus sequence, or even if you're not an economics major, maybe it's one of those classes that you're required to take, well, or business, I don't know. Well, this idea also applies to business and economics. So C is the cost of producing X units of whatever thing, and well, then the marginal cost is the derivative. That is how much the marginal cost is in this case. Let me read. I think it's dc dt. How much is the cost changing with respect to time? Well, if we integrate, we can find out the net change in the cost within for producing x2 minus and between x1 and x2 units of a particular product. However, the one that we're interested in is the one that in which we discussed back in the derivative chapter, when we were relating the derivative to essentially the distance and velocity problem, or the distance and speed problem. Well, the speed is something else. Well, you'll see. And essentially, so we have an object moving at a straight line. That's the simplest case, all right? And with a function s of t. And its velocity, of course, will be the derivative of s, all right? Now, if we integrate the velocity, we retrieve the position function. So the net change in this situation is going to tell us how far did the object move between t1 and t2, all right? Now, here is the thing. Let's recall that there's a big difference between velocity and speed. And and at the same time, together, there's a huge difference between displacement and distance, all right? Well, distance, for example, let me give you an example. So we want to go from point A to point B. Well, the distance is the shortest distance traveled from A to B, and it's actually a distance as a straight line. So that is the difference between the position for AB minus the position in the point A. However, displacement is something totally different. So because in this case we can go from point A to B, we can go to the left and then go south, then go to the left again, go south, go to the right, go to the east, go north, go west, go north, and reach B by going east again. And well, in this case, the total displacement will be the addition of all these distances: 1, 2, 3, 4, 5, 6, 7, 8, 9. We would have to add 9 total distances in this case. So that's the huge difference between displacement and what's it called, and distance. So this is the, whoops, I wanted to highlight first. So this is displacement, and this is the distance, really. All right, and there's many ways to go from point A to B. Well, I just chose a random way, and of course the distance there, it's unique, just as a straight line. What does that have anything to do with integrals? Well, so we're gonna start with a velocity function. So when we integrate the velocity function, we will be retrieving the position function s of t. However, when we perform the integration, well, from the geometric point of view, the integration is going to give us the area under the curve. and bounded below by the x-axis, or if the area lies below the x-axis, it's bounded above by the x-axis and below by whatever curve, as you can see from this picture right here. And yes, we're gonna get into some funky situations in here. So let me erase this. So in this case, the total distance traveled, it's actually, well, I think I mentioned the reverse concept. Distance is the total distance traveled in different direction, and the displacement is just from A to B in a straight line. So in this case, if we want to find the distance, okay, let me do the displacement first. Displacement, that'll be area 1 minus area 2 plus area 3. So in this case, we would be subtracting these negative distances, you know. However, when it comes to finding the total distance, so in this case, give me 1 second. You need to see a picture here. All right. So in this case, well, we need to take those distances as absolute values of distances because, again, well, so here I'm at the origin. I'm going to do 1, 2, 3 steps, and then I'm going to take back 1, 2, 3, 4, 5. So my total distance was 3 plus 5, which is 8 steps. However, my displacement was only, what was that, negative 3? Right, negative 3, that's a negative distance in the end, all right? So in this case, for distance, this area right here, we will need to make it positive in order to find the distance, and that is area 1 plus area 2 plus area 3, all right? So, and in this case, that's positive distances. So, as an example, so we have a particle that moves along a line so that its velocity is given at time t is given by the function v of t equals to t squared minus t minus 6, measured in meters per second. Number one, they're asking us to find the displacement, and they're also asking us to find the total distance traveled. So the displacement is the distance, the final position minus initial position, and in this case, regardless of the route that you took to get from point A to point B. Well, that is, in this case, well, displacement will be S of 4 minus S of 1. All right, that is the position at 4 minus the position at 1, but we don't have the position. We don't know the position. We know the velocity, but we can get the position from the velocity by integrating. That is the integral from 1 to 4 of the velocity function, which in this case is t squared minus t minus 6 dt, and integrate every single term. So that's going to be t cubed over 3 minus t squared over 2 minus 6t, evaluated from 1 to 4. All right? So here is the thing. Well, I would like to save some time in this case and just give you the answer. So in this case, well, let me just set up at least the fundamental theorem. So that's 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. And well, that should give us 9 halves. Actually, negative 9 halves. All right? So that's going to be the displacement in this case. And well, I'll show you in a second why are we getting a negative value. So I'm going to move to the graphing calculator here. And according to my notes, okay. And I'm going to graph this function. So we're going to go to y equals, well, I already typed the function, x squared minus x minus 6. And let me graph this. So we are integrating between 1 and, so 1, 2, 3, 4. Do you see how the area between 3 and 4, which is positive, is smaller than the area between 1 and 3, which is a lot bigger? That's why we're getting a negative value in this case. So actually, let me draw this in our paper. So this will be, no, it's actually 3. So we want the area between, actually, okay, I'm gonna do it in green for the positive and red for the negative area. And well, clearly from the picture, the area below the x-axis is larger. The negative area is larger than the area above the x-axis. So that's why we're getting a positive, a negative area in the end, a negative displacement. So in other words, this particle is essentially moving in the left direction. It's moving backwards. That's how we interpret this result. They're asking us to find the distance now. So for the distance, that's going to be the integral of the absolute value of t. In this case, remember what I did with my steps here. So in this case, all those steps that I did in the negative direction, I'm still counting them as positive steps and everything else. So I did 3 steps to the right and 5 steps to the left. So in this case, I added up to 8 steps in this case. So in this case, it's going to be the same situation. But what's going to happen? This negative area here, I'm going to draw the graph again so you can see the visual of this. So essentially, so 1, 2, 3, 4, 5. So that's at 3 goes like this, and it's going to go like this between 1. So now we are going to have only positive areas. Positive areas mean a positive displacement in this case again. So whatever I did backwards, that is in the negative direction, I'm going to count it as positive number of steps, even though I'm going backwards. So that's the same situation with this function. But in this case, one thing to notice in this case is that, okay, from the graph, the function is negative. It's negative between 1 and 3, and it's positive between it's positive between 3 and 4. And we need to be careful how we set up this idea. So because of absolute value bars, okay, in general, let's go back and review the definition for absolute value. So absolute value of x equals negative x for x less than 0 for negative values, and x for x greater than or equal to 0. Essentially, that's the V-shaped graph, right? It's the line with negative slope for negative values of x, and the line with positive slope for positive values of x. In the same idea, we are going to, in this case, define our absolute value of t squared minus t minus 6. So that's going to be number 1, negative polynomial and positive polynomial. Negative t squared minus t minus 6. And in this case, we know the graph of this parabola is negative. In this case, well, within our interval for t between 1 and 3. Of course, It's also negative at other values, but we care only about the interval between 1 and 4. And it's going to be positive t squared minus t minus 6 for t going, in this case, between, I would like to say 3 open, t close to 4. But anyway, these two get connected. So I'm going to use the same limits of integration. So in this case, number 1, that means we are going to set up the integral like this. That's going to be the integral from 1 to 4 of the absolute value of b of t. We still start with that. But in this case, well, we're going to split this integral into two integrals. That is, the integral of negative v of t dt, but we know that the negative part goes between 1 and 3, plus the integral of v of t, the positive part, which goes from 3 to 4. All right? And dt. Don't forget the dt. So in this case, well, red for the negative and green for the positive. So I'm going to continue over here. That's going to be the integral from 1 to 3 of negative t squared minus t minus 6 dt plus the integral from 3 to 4 of t squared minus t minus 6. And all I'm going to do here is simplify the first integral, the one that contains the negative function. That's going to be the integral of 6 plus t minus t squared dt from 1 to 3, and plus the integral from 3 to 4 of t squared minus t minus 6. And well, for this situation, I will just give you the result because well, we have already practiced a lot on integration, and I'd rather move on to the next method of integration, which is really the core part of this course, the tool that you need to sharpen very, very well for calculus 2 and well every consecutive mathematics course. I mean, this one is going to take, I guess, 10 or 15 minutes to simplify. So that's going to give us a total of 61 over 6. In fact, this is the same example as on the textbook, which is approximately 10.17 meters. So in this case, we're looking at the distance. How much distance did we travel regardless of the direction? In this case, all the distance is in the positive direction. All right. Okay, so let's move on to the next and last section. And by the way, I gave you the PDF file last night on Canvas only for the first part of it. This one is going to be possibly the longest section we're going to cover. All right, and that's the method of substitution. So, or the substitution rule. All right. Number 1, before getting into the method, let's explain briefly where is this method coming from. All right. So find the derivative of f of x equals 5x cubed minus 3 to the 7th power. The question: how do we differentiate this function? Which differentiation rule do we use? Anyone? The chain rule, right? Because we have a composite function. So let's differentiate this f prime of x equals to the same quantity 5x cubed minus 3, 7 times 7 minus 1 times the derivative of the inside, which is 15x squared. And that reduces to, what's 15 times 7? So that's 5, carry 3. That's 85, so that's going to be 85 x squared times 5x cubed minus 3 to the 6th power. All right? So that'll be the derivative of this function using the chain rule. Now, this implies that the integral of 85 x squared times 5x cubed minus 3 to the 6th power with respect x, well, because the integral and the derivative are opposite operations or are inverse operations, well, essentially we are going back to the original function. So this implies that the integral of this madness is this original function 5x cubed minus 3 plus 7, but of course a plus c, right? I mean, over here we have a plus 0 essentially. That's the constant of integration, if you will. However, we could have had a plus 5, a minus 7, or whatever number that you like. So that's the implication. Now, well, of course, some of you have taken calculus before, whether you're retaking the course or you have taken it in high school. You know what happened from here to here. But again, let's pretend that we don't know anything about it. So how do we go from here to here, all right? Well, in this case, I got it like this because I know this integrand right here came from differentiating the original function. But what if I didn't know any of this and I was given only this? How do we go about it? Well, so the method of substitution essentially is the chain rule equivalent of the integration. So it's the chain rule backwards, you know. So, but we need another. We need to know how do we do that? Well, now, for example, well, what about the integral of simply x squared 5x cubed minus 3 to the 6th power dx? Well, in this case, I cannot say that this is the same result, and that's because of the coefficient 85, right? So what about, for example, the integral of 3x squared 5x cubed minus 3 to the 6th power dx? Well, I mean, the integral of this will take us back to this function, but the integral, when we have the 3 and not the 85, will take us back to a similar but a slightly different one. It's a slightly different function. So in this case, we cannot guess. I mean, we could sort of guess, but guessing is not going to be an efficient way to find the integral for this function. So we need a systematic way to get this done. Now, so that's like the question, like the motivation of why do we do the U substitution. Let's get even more motivation. Now let's consider these two integrals. So the first integral, well, we already did an integral that is similar to the first integral, and well, this one have about doing some algebra. Expand the binomial, that is 9x squared plus 2 times the product of the 2, that's 3 times 4, that's 12, times 2, that's 24, x plus 16 dx, and integrate each term, that's 9x cubed over 3 plus 24x squared over 2 plus 16x plus c. Well, that reduces to 3x cubed plus 12x squared plus 16x plus c. This one was okay to do. I mean, expanding a binomial square that is foiling twice, well, doesn't take too long, all right? However, what about this same integral, but instead of raising to the power 2, I'm going to raise this to the power 23. Do you feel like expanding a binomial of a power 3? Do you feel like foiling 23 times? No, and in fact we're going to do it. I mean, what about the integral of 3x plus 4 to the power 1756 dx? No, we're not going to FOIL 1756 times to integrate 757 terms. No, we're not going to do that. We're going to use substitution to integrate this in a blink of an eye. All right? So again, this one is okay to do, to expand the binomial, integrate three terms. That's fine. That's not that bad. However, larger powers and also when we have radicals or other kinds of functions, that's just not possible to do. So let's define the substitution rule in this case. So essentially, we're going to have a function u, which is our g of x that we are going to integrate. So it's this one right here, and that's the function. So we're going to have a composition function. So we will integrate some f, and we're going to find a clever substitution. And well, notice this integral right here, how it has a lot of symbols, a lot of functions, composition function. So we are going to turn that function into a simpler function that is the integral of f of u du. And that u will be the game changer to turn this madness right here into something really short to integrate. And well, how about we go about the examples? I mean, this is the formal definition. It's very symbolic, but I guess seeing it in action would be a lot better. And guys, for the first few examples, I will discuss three different ways to carry the substitution. And the reason why I will cover the three different ways in the end is that's because, well, if you look at other resources on the internet or other textbooks, different authors carry the substitution in different ways. And I am aware of at least three different ways to perform the substitution. For the first few examples, again, I'm going to do it the three ways, but in the end, I will stick to only one version. But in the end, you guys are free to use the way that you feel more comfortable with. Okay? All right. So, let's see. Oh, table of integrals. This table of integrals, it's exactly the same as the one I gave you in the previous section, but what's different? The difference here is, well, minus this formula. Okay, let me, we don't need this formula actually. Only the remaining ones. The only difference between this mini table and the one I gave you in the previous section is that we no longer have x, we have u's in this case. We have the letter u, and we integrate with respect u, because that u is what's going to make the u substitution in this case, right? So, but essentially the rules will be exactly the same. All right. Okay. So here is the thing. One thing to recognize as a pattern, so some pattern recognition here, whenever we have a more complex integral, so typically inside of the parentheses, or as the exponent of an exponential, or as the radicand of a radical, we are going to have something whose degree is one higher than the quantity that multiplies outside. That's because of the chain rule. When we do the chain rule, we do that differentiation of a polynomial. When we differentiate a polynomial, we get a 1 degree lower than what we had inside of the parentheses. So that's the pattern that you want to follow when, or that you want to identify when dealing with the substitution method. All right. So let's see. Let's see, we have this pattern over here. What's the degree inside of the parentheses? 2. Okay, outside of the parentheses, we have an x multiplying with the dx. What's the degree of that x? What is that again? Loud. I can't hear very well. The degree of this x. 1, all right? It's an invisible 1. Okay, so this 1 degree looks like the derivative of something square, right? The derivative of a cube gives us 1 degree less, a square. The derivative of a fifth power gives us 1 degree less, which is a fourth power. The derivative of a 17th power is 1 degree less, which is x to the 16. This is the pattern that you need to follow in order to perform the substitution. And typically, what we do is set the most complicated part of the integral. Well, what do I mean by the most complicated? That is quantity inside of parentheses, quantity inside of a radical, quantity in the exponent of an exponential function, or as an angle of a trigonometric function. Hopefully, well, you'll recognize this pattern very well soon. All right. So I'm going to do the first method. And the first method is actually the method that I will stick to in subsequent problems. So method number one. So the method number one is to set, well, u equal to x squared minus 12. So we need to find the differential of u, that is du, the derivative of x squared, which is 2x, dx. All right. Now, notice in this case, outside of the parentheses, I have this x dx. I have this x dx right here, x dx. However, in this setup I did, I will have to solve for x dx. So I'm going to turn this into x dx. Whoops. X dx equals 1/2 du. And we're ready to do the substitution because, number one, this integral, this whole thing, x squared minus 12, becomes the u to the 4th power, and this quantity x dx, that's 1/2 du. Every constant factors, I'm going to take them outside of the integral. That's 1/2 the integral of u to the 4th power du. Notice how this integral looks a lot simple. So let's just integrate u to the 4, that is 1/2 u to the 5th over 5 plus c. So we're essentially done with the integration. However, now, number one, we need to simplify that 1/2 times 1/5. That's going to give us a 1/10. And at the same time, I'm going to back substitute for u, because this is what we're essentially doing. We are working on a problem in the world of x that is a complicated problem. What we're doing is send the problem to the world of u to simplify the problem. We solved the problem in the world of u, which, as you can tell, it was really easy to solve. But now that we solved the problem, let's go back to the world of x. And that's final answer. All right. Let me discuss the second way to show the substitution. Number two. And let me write the integral again. The integral of x squared minus 12 to the 4th power dx. And in this case, okay, this is what I'm going to do. U equals to x squared minus 12. So the choice of u, it's not going to change regardless of the method that you go about. All right. So du will be 2x dx. All right. So I'm missing an x right here, right? X dx. Which one? X4 plus 12, right? Yeah, thank you. Okay, so this method, this second way to go about the substitution is the make-a-wish way, if you will. All right, because what do we have over here when we set up the du part? What's du? 2x dx, all right? What do we have over here? X dx only. Do these two quantities match? What is missing here, so it looks like this? So we wish we had a factor of 2, right? But we don't have it. We can make our wish come true by multiplying by 2. Okay, multiply by 2. However, if I just multiply by 2, I will be duplicating the value of the integral. We need to do the reverse of multiplying by 2. What's the reverse of multiplying by 2? So divide 1 outside of the integral. Because essentially we are multiplying by 1. What happens when we multiply any quantity by 1? It remains the same. And there's many ways to represent the number 1. The number 1 can be 2 over 2, 5 over 5, 7 over 7, your favorite number, your favorite combination of numbers. In this case, we're looking for the convenient version of 1 that matches our substitution. So in this case, this whole thing becomes du, and this whole thing is u. And, well, that's 1/2 the integral of u to the 4th du, which essentially, isn't it the same as that we got before? All right? And, well, that's 1/10 u to the 5th plus c, and 1/10 x squared minus 12 to the 5th power plus c. Same result. Different way to go about it. Let me discuss the third method. The third method is not very common. But what I've noticed from students in the past, they either use method 1 or method 2. Either way, it's fine, or even the third method. So let me call this method 2. Method 3. And so for method 3, let me write down the integral again. The integral of x squared minus 12 to the 4th power x dx. And the choice of u will be exactly the same. That is, u equals to x squared minus 12 du equals to 2x dx. Okay? Well, for this third method, what we're going to do is to solve this last equation for the dx quantity. That is, divide both sides by 2x. Dx equals du over 2x. Okay? And this is all we're going to do here. In this case, I'm going to replace dx, which is du to 2x over 2x, only here, only to the 2x, and this x that we have here, leave it alone. You'll see what's going to happen. So number 1, that's the integral of the quantity u, which we already said, u to the 4th power, times x, this whole x right here, and this dx will become du over 2x. So this is where the magic comes, right? In this case, notice how these x's cancel, and in the end, we have to have an integral that only depends on u, du over 2, and while this 2 in the denominator is essentially a 1/2. Isn't that the same integral that we're evaluating in the world of u? So my intention, guys, is not to confuse you with showing you 3 different methods. My intention is that you get to choose the one that you feel more comfortable with, the one that you feel that you like better. I know in the end we should get the same result, the same answer. I mean, you can solve for x dx, you can do the make-a-wish method, or you can solve the equation for dx. In the end, it's the same, it's going to be the same thing, right?